All right, so let's take a look at calculating the pH/pOH of solutions with strong acids and bases. So when you're talking about strong acids and bases, defining the pH is relatively simple. And it's relatively simple because strong acids and bases fully ionize. And so the concentration of H plus slash OH minus is approximately equal. I will just say equal to the concentration of the acid slash base. And for base, we'll put a little kind of star here. And this isn't actually totally true, and we'll see why in a little minute. Bases are slightly a little bit tricky. So let's take a look at some examples. So for example, find the pH of a 6.0 molar HCl solution, right? So 6.0 molar HCl. And so I can tell you straight away, HCl is a strong acid. Later on, we'll learn how to identify strong versus weak, but for right now, I'll just tell you. And then the other thing that you have to realize about these types of problems is that we assume that the concentration of H plus and OH minus in the water before you add the acid or base is negligible. It's equal to 1 times 10 to the negative 7, but that's so small compared to the numbers that we're working with that it won't make a difference. So, but here, assume concentration of H plus slash OH minus in water is negligible, right? It's just kind of too small to really make a difference. And so all of these things can be done with rice table problems. With these strong acids and bases, the rice tables aren't totally necessary, but I still think it's a good idea to go ahead and write them out so that you know what's going on. And so in this case, I didn't give you the equation with strong acids or any acids or bases. You should be able to write the chemical equation yourself. So we're talking about water, so we're talking about HCl reacting with water to form H3O plus and chloride minus. So you should be able to write this equation out. One of the main things that you really want to pay attention to is this arrow. This is a one-way arrow. It's complete ionization. So let's take a look at this data here. So we have the 6.0 molar. That's our concentration of our HCl. Remember, water is a liquid, so we're just going to ignore it throughout the whole table. We're going to assume that this is negligible. So we're going to say it's approximately 0. And then we're going to go from the left to right. So this will be minus x, this will be plus x, this will be plus x, and then this will be 6.0 minus x, this will be x, and this will be x as well. Now, the reason that these rice tables are kind of very, very simple is because of this one-way arrow, right? All 6 molar of this HCl is all going to become H plus, right? And so it's pretty easy to tell right away. Since we have this complete arrow, all of this is going to dissociate. So we know X is equal to 6.0 molar. And since X is equal to the concentration of H plus, we can figure out the pH pretty easily. Remember that the pH is equal to the negative log of the concentration of H plus. And so we have that already. And so we just take that in here, plug it in. If you plug in 6 molar here, you should get a negative 0.78, right? So you see the pH here can indeed be negative, and so this solution is acidic. So you see you can do the rice table, but overall it's relatively straightforward. Let's take a look at a more complex example with some kind of more tricky stuff in here. So we'll say, what about a solution of, or a solution, we'll say with 100 ml of 3.0 molar, and we'll go with calcium. Let's go with barium hydroxide. This example is not too realistic because barium hydroxide isn't that soluble. but whatever. It'll show my point here. So barium hydroxide is a strong base. Again, later on, we'll learn how to identify these. For now, I'll just tell you that. So you have 100 mils of this solution with 400 mLs of water. And it wants to know what the pH is, right? And so the first thing we need to do is we need to find the concentration of our barium hydroxide. So we have 100 mils of this, 400 mils of water. We're talking about dilutions of solutions, right? And so we can write M1V1 equals M2V2. And so our initial concentration is this 3 molar. Originally, we have 100 mils of it. And then if you think about what our final volume is, well, we had 100 mils. We mixed it with 4 more 100. That's going to be 500 ml, right? And so then we can reorganize this equation to solve for M2. So divide both sides by V2. So we got M1V1 over V2. And then we plug in our stuff here, right? This is 3.0 molar. Let's see, V1 is 100 ml or 0.1 liter. And then the V2 is 500 ml or 0.5 liters. It doesn't matter because this mLs cancel out. So you get the same thing whether you put liters or milliliters. And then simply do the math here. You get 0.6 molar of barium hydroxide. And so now we need to think about how we're going to find the pH, right? In this chapter, last chapter said if you don't know what you're doing, start off with a rice table. So let's get our rice table going. And so for barium hydroxide, we can say that the barium hydroxide will dissociate completely into 1 barium and 2 hydroxides, right? So you can include water in this equation. You cannot include water in this equation. It doesn't really matter. It's a liquid, so you're going to ignore it anyways. And so we now see that our concentration of our barium hydroxide is 0.6 molar. This will then be over here plus X, and this will be plus, we'll assume 0 dissociation initially, and then the change, we're going to get rid of some barium hydroxide, and we're going to form some plus X of barium, and then plus 2X of the barium hydroxide. So that's kind of where you got to be careful with these bases. Some will donate 1 hydroxide or accept 1 H plus. Some will donate 2 hydroxides or accept 2 H pluses. And so then we can do 0.6 minus X, X to X. And then here, because this is a one-way arrow, because this is a strong base, this will completely ionize, right? And so you know that this value ends up being 0, right? There's no barium hydroxide at the end. There should be 0.6 molar of this. And then when you're thinking about what does that mean about the concentration of hydroxides, there's actually 2 for every 1 barium, right? So kind of X here is equal to 0.6. So 2X is equal to 1.2 molar, which is the concentration of the hydroxide. And then I think our problem originally asked for the pH. So we got to figure out the pH of this solution. And so remember, POH is equal to the negative log of the concentration of hydroxide. So we can take that into here. And then if you plug that into your calculator, let's see, negative log of 1.2, you get a negative 0.079, right? POH. And then remember that pH plus POH is equal to 14. And so you can take this negative 0.079, plug it in for POH and solve for pH. And so your pH here is, in this case, 14.079, which is obviously greater than 7. And so this solution is basic, which is what you would expect by adding a strong base. So again, it's all just about knowing how to do these rice tables. And then the trick to knowing these kinds of problems is knowing that these strong bases completely ionize.